Hi, in this lesson, I want to talk about meteorites, and in particular, how meteorites can unlock the secrets of the Earth. In particular, the really hard to reach bits, either from deep within the Earth or from the very early Earth. Okay, we need to start by just clarifying what we mean by some of these terms. Let's start with this idea of a meteor. Now, you may have looked up at the night sky and seen shooting stars, um, little flashes of light across the sky at night. These are little bits of rock, some of them the size of a sand grain, hitting the atmosphere, the friction causing light and heat, and most of the time they'll just burn up. Meteorites, then, are where we have some of that rock actually making it to the Earth's surface. Now, there are three basic types of meteorite. More if you want to split them, but there are three basic ones that we need to be aware of. Firstly, what we call stony meteorites, then stony iron meteorites, and finally, iron meteorites. Let's have a look at each of these in turn. These meteorites don't fall in equal amounts. The vast majority of meteorites that fall are stony meteorites. We then have a small percentage of iron meteorites and a tiny percentage of stony iron ones. Yet each of them can give us valuable clues about the Earth. Let's start by looking at the stony meteorites. These are made of rock, as the name would suggest. So it's silicate material, density of around 3, so similar to a sort of mafic igneous rock. The biggest issue with them is they look like rocks. Unless you really know what you're looking for, your chances of finding a meteorite in most places is pretty low. And most of the meteorites that fall are this type. If you have a look at what one looks like, you can see that they're crystalline. They look like igneous rocks. There are some that have some distinctive features. Most of them have these features called chondrules. These little sort of glassy structures, quite small scale, and they're sort of solidified droplets. I suppose the equivalent would be tektites or Pele's tears on Earth. These are old. These are the things that we can date to give us an age for the Earth. These form at the same time planets are forming. Stony iron meteorites are really unusual. It's only maybe at most 1% of meteorites are like this. And these are a mixture, as the name would suggest. So we get some iron and nickel in it, and we get some silicate minerals. If we look at what these look like, we see some crystals of olivine, high temperature, high pressure mineral, and then crystals as well of a mineral called camosite, which is an iron nickel alloy. These things are quite unusual. We think these represent a transition between stony material and iron material. So the boundary between the two. Iron meteorites, as the name would suggest, are made of iron. It's only a small percentage of meteorites that are this type, but they do find a lot of the ones that are found worldwide. They are a bit more distinctive. They're also they can be found with metal detecting equipment. They're also really quite beautiful. and they're really quite dense material. We'll come back to this idea of a differentiated body in a moment. This is a picture of an iron meteorite. Um, they have this iron and nickel composition. They tend to have quite a smooth outer surface, maybe slightly scalloped, because of the friction with the atmosphere. As it's tumbling through the atmosphere, it gets abraded away because of the friction. If we look at inside one of these, we can see these amazing crystalline patterns. They're called Widmanstatten patterns. And they show that these things have cooled really quite slowly. Now, finding meteorites can be a quite specialist job. There are people who do this for a living, either to sell them to collectors. There's quite a big collector's market for meteorites. Also, academics are going to be looking for these because of the clues they can give us. Best place to go and find these, well, Antarctica is a very good place to find them. They stick out on the ice. Other places you can that are good for meteorite hunting would be places like the Australian desert, where sort of rocks that don't fit in, really stick out and make them easy to find. But we need to think about why these things are important. What clues are we getting about the Earth from meteorites? They can tell us how old the Earth is. There's no rocks on the Earth's surface that we can date to give us an age of the formation of the Earth, because we have an active crust. We have plate tectonics, we have erosion, we have recycling of rock. So the oldest rocks that we have on the Earth's surface go back about 4.2 billion years. So there's a bit missing. Meteorites, though, haven't been changed. They're the materials that the Earth was made up of. They're the bits left over, if you like, still flying around space that didn't coagulate to make a planet. So if we can date those meteorites, and meteorites give us a very consistent set of ages, we can also date the Earth. Because when the meteorites were forming, that's when the Earth was forming. And particularly by dating these chondrules that are in there. So we get the age of the Earth, but they also tell us, or suggest, should I say, the composition of the Earth's core. Meteorites are made of the same stuff as the Earth. If we try and make connections, the stony meteorites might represent the Earth's mantle and crust. The iron meteorites represent the core material. Maybe there's fewer of those flying around as well, because their greatest density would have made them more likely to become incorporated into planets. When they do become incorporated into planets, the materials differentiate themselves. They sort themselves out by their density. But we can't find core material anywhere on the Earth's surface. It's just too deep. It's too dense. It does not make it to the surface. So meteorites give us one of the strongest pieces of evidence we have for our iron-rich core. If this stuff is flying around in space as a meteorite, it must have formed planets as well. It must form the core of this material. These things are too dense just to have been left out completely from planetary formation. I mean, if we go wild and start to speculate, some of the carbon that we can find in some of these, some rare meteorites, may have been the Kickstarter for life, but that might be pushing things, a bit beyond the evidence that we have. If you want to go and see a meteorite, you can. A couple of the good places to see. You could go to Arizona. This is a fairly recent, it's about 70,000 years old, meteorite impact crater. Because it's fairly recent, it's quite, it's nice and clear in terms of what it is. It's quite a small one. It's about 1 kilometre across. It was probably made by an impactor that was maybe about 40 metres across. So not a massive meteorite. If that's a little bit too far away, closer to home, you can go and find a meteorite in the Evolution of Whales exhibit at the National Museum in Cardiff. Okay, if you go and, like this person, go and touch that meteorite, which you're welcome to do in the museum, it will be the oldest thing that you have ever touched and will be the oldest thing you can ever touch. So, as we see the sunset of the meteorite crater in Arizona, the evidence that we have for the internal composition of the Earth, to actually have the materials that make up our deep Earth in our hand, with the ability to put through chemical analysis, to look down a microscope at thin sections of, we must use meteorites. Those materials are completely inaccessible to us as geologists on the surface. The clues that we get from these quite incredible materials are immensely valuable. Now, meteorites aren't the only bit of evidence that we have that suggest the internal composition of the Earth. But discussion of those, I think, is a topic for another lesson. I'll see you then.